Hello, today we are going to do our second lab experiment, which is electric field mapping. So this is an introduction, and then there's another longer video file with the procedure, and there are also going to be two JPEG files that are attached with this, in addition to the write-up from the lab manual. So I'll post the PDF of that with this as well. But let's go into an overall summary of what the lab is. So we're beginning by talking about the electric field, that the electric field is basically a measure of the force acting on a test charge within the field divided by the charge of that test charge. So F divided by Q, newtons per coulomb. And if the test charge is positive, F and E point in the same direction. If the test charge is negative, the electric force points in the opposite direction to the electric field. The electric field vector ultimately only depends on the source charges. It does not depend on the test charges, which means it exists whether or there is a test charge moving in the field or not. Now we are going to not measure the electric field directly, but we are going to infer some information about the electric fields in a couple of different charge configurations by looking at the electric potential. And so the electric field is force per test charge. The electric potential is potential energy per test charge. So a charge that's moving within an electric field is going to have a change in the electric potential. And so we call the change in electric potential, we define that as delta V. The electric potential only depends on the source charges. So saying a charge moves through an electric field and saying a charge moves through a potential difference are equivalent things. We are going to determine the electric field first by finding equipotential lines. So basically lines of constant potential. And the electric field is going to be perpendicular to the equipotential lines. And so once you draw the equipotential lines, you'll be able to infer the electric field lines because they cross the equipotentials at 90-degree angles. And they also come out of the positive charge and into the negative charge. So here's a quick summary of the procedure. We're going to be working with conducting paper. If you notice in the film clip I did, the conducting paper is black, and so I used white chalk on a black surface. The JPEGs you'll be downloading have black markings on a white surface. Basically what I did was I inverted the photos that I took because it's actually quite a bit easier to work with the inverted photos. Basically what I want you to do is make a printout, or rather if you can annotate electronically, that's fine too. You need an electrical pen to do that. Otherwise, print it out and take a picture of what you do. But you're going to draw the equipotential lines based on the points that I marked. And then once you have the equipotential lines, you're going to draw the electric field lines. Remember, the electric field lines come out of positive into negative, and they cross the equipotentials at 90-degree angles. And so we're going to do two different charge configurations. One is basically a dipole. We have a positive charge and a negative charge. And the other is we have two lines of charge. So we have a positive line of charge and a negative line of charge. So we have a positive and negative point charges and positive and negative lines of charges. And so you'll see how the equipotentials look different in those configurations, and correspondingly, the electric field lines will look different in those configurations. But what you're going to do is draw the equipotential lines, and if you're not sure what point corresponds to what potential, pay attention to the other video because I'm going to go through it point by point for each distribution. And so you should be able to tell which point corresponds to which potential, and then mark down 2 volts, 4 volts, 6 volts, and 8 volts, and then draw the field lines accordingly. So how does this work? You have the conducting paper, you have your 2 points, which are basically pennies, and for the lines, you have 2 metal bars that you can place over the pennies so that you have lines connected. And so we have a power supply, which is outputting 10 volts. And so we're going to connect the positive end to one penny and the negative end to the other penny. And so the conducting paper allows some current to flow through so that there's a potential difference between the positive and negative terminals, and that there's the potential difference changes with the position you have on the paper. So you set the potential difference at the power supply to 10 volts, and you should be able to measure that there's 10 volts between the 2 pennies. And if everything is connected right, when you move you'll keep the negative terminal in place. And so if you move a wire that's connected to the positive terminal, you'll be able to see how the potential difference changes with location. And so you'll find points where the potential is 2 volts, and you mark those points. You do the same for 4 volts, you do the same for 6 volts, you do the same for 8 volts. And again, you're going to draw the equipotential lines in. And we don't actually have carbon paper for this. I didn't take everything out of the labs that I wanted to. So what I improvised, and I used some chalk to mark the points. And like I said, I inverted the images of the conducting paper. And so that's what you're going to download and work with. So for the 2 lines of charge, you're going to pick points along the field line, and delta V you'll know. You might as well pick 2 points along the equipotential and then measure S, the distance from the between the 2 points. And so basically just draw 2 points along the equipotential lines once you draw them. And that'll give you a measure of the electric field, and or at least the electric field between those 2 points. And so you basically do that going from 0 to 10 with both distributions. So do it for both distributions. So just basically, you start with the negative terminal, pick a point at 2 volts on the 2 volt equipotential line, measure that distance, that gives you a value for the electric field, then go on to 4, measure that distance, that's the electric field, and then go on to 6. You probably see some variability doing that for the point charges, but with the line charges, they should be fairly uniform. So we do that for both charges, or for both charge distributions. So these, so I want you to calculate the field strength, and again, for the parallel plates, you should get a fairly uniform field strength. For the point charges, it's going to be a little different than that. But then you're going to ask, where is the field weakest in the dipole distribution and where is it strongest? So again, with the plates or the lines of charge, you should get a fairly uniform distribution. You should have a more noticeable difference in the field strength when you're looking at the point charges. And so answer those questions for your lab report. So this is the inverted image of the point charges. So the black markings are where I mark the chalk. And so again, you'll need to double check to make sure which points correspond to which voltage, then draw the equipotential lines accordingly, and then draw the electric field lines. So remember, the electric field lines go out of positive into negative, and they intersect the equipotentials at angles of 90 degrees. So this is the point charges. You see the 2 pennies here. And then here you have the line charges. So these are your sheets of charge. And I extended them a little, the measurements a little bit beyond the edges. If you remember, if you've done, I don't know if you've looked at the Gauss's law lecture yet, but that'll tell you something about how infinite sheets of charge look. And that approximation works well if you're not close to the edge, edge of the edge of the sheets. And so you can sort of see that in this diagram. Again, make sure you know which points correspond to which potential, and then draw the equipotentials in, and then you're going from positive to negative and intersecting at 90 degrees. So that's this lab. And again, so there's going to be the much longer video with the procedure, and I'm going to post the instructions from the actual lab manual, and I'm also going to post the picture files for these two charge configurations. So you'll have these and be able to work with these. So if you have any questions, don't hesitate to email me. I apologize if I've been slow on the emails. The last day or two, I've had quite a bit of work, but I will respond to your emails. Just please be patient. And again, I apologize if I was slow for a couple of you. Okay, thank you very much, and I'll see you next time.